So I'll kick things off. Just we've got a few attendees join now, so we can make a start.
Yeah.
So apologies again to those that have joined us for the morning. Just a quick recap. Obviously, for those that are just joining us, thank you very much for what is the SCT Spring Lecture, now online. Obviously, apologies, this was originally planned for face-to-face, but we shifted to online just, for the needs of our members, just to kind of ensure we still make this happen. We will ask for a little bit of feedback kind of post. We'll be sending out a bit of a survey just to see what we do moving forwards, what works best for you and current climate. But either way, we're here today, and shortly I'll introduce Keith properly in the presentation we're about to see. From a setup point of view, so once I have handed over, Keith's got a short presentation to run through. There will be a Q&A opportunity at the end. From a questions perspective, just fire these in via the chat function in Zoom. Just make sure you're addressed to panelists and I'll be able to see them. I'll queue them up and I will relay them to Keith at the end. There's also the Q&A functionality in Zoom as well. So I'll do a bit of an intro, first of all, Keith, to you. I've got a quick bio to run through for you, and then a short abstract for what you're about to talk us through, and then I'll hand over and the floor will be yours. So, hi, first of all, bear with me. Just got to read these off paper. I haven't learned these off by heart. So, Keith Mothersdale has worked in the broadband Cat-V engineering, design and development for over 25 years. Currently, he's in charge of technology, engineering, design and innovation within the last mile broadband product division within Amphenol Broadband Solutions. In 2013, Mr. Mothersdale was presented with an honorary fellowship to the UK SCT organisation in recognition of his long-term technical contribution to the Cat-V industry. Prior to joining Amphenol, he worked at Telest, heading up engineering, design and development within the passives and indoor division. Prior to Telest, he worked at the Technetics Group as CTO, focusing on product roadmaps, product innovation and all aspects of engineering. He has written several industry white papers and presented at several major broadband forums around the world. He has written and had published over 6 patents relating to product innovations. He holds a B Engineering Honours degree in Electrical and Electronic Engineering and MBA from University of Bradford. Quite the intro. And then on to what we're about to hear from. So obviously titles on the screen, but broadband cable connectorisation, the next evolution has arrived. Short abstract. So HFC plant and home cable connectorisation has remained one of the most challenging parts of the end-to-end broadband HFC network. Year on year, millions of connectors are replaced. Intermittent faults remain a constant challenge. Customer quality of service has now become more important than ever for broadband providers, as the broadband is now seen as a major part of day-to-day home and business users. After several years of groundbreaking research and thinking outside the box, Amphenol will demonstrate the new connectorisation evolution with an intriguing presentation of the new cable interconnect breakthrough. That's all for me. Keith, the floor is yours.
Thanks, James. Hello, everybody. It seems a bit strange. I was looking forward to standing at the front of a cinema. Never done that before, but never mind. Hopefully we'll be able to meet up soon. So yes, the evolution as it stands now has arrived, a new connector. Before I started, I just want to let you know, I live in the middle of nowhere, and I'm in the Yorkshire Dales, the North Yorkshire Dales, up in the northwest of England near the lakes. And what you see on the screen right now is my home broadband internet speed. But there's a few people looking at that with quite amazement. Yeah, and here we get guaranteed 1000 megabit down and 1000 megabit up load, guaranteed for £30 a month. As I'm a volunteer volunteer with Barn Broadband for the rural north, I have the privilege of utilising their 10 gigabit service. So what you see there, hopefully my service is fast enough to deliver the video stream here. Okay, so the coaxial cable connector interconnect, it's been and is a thorn in the side of broadband cable operators around the world without exception. It's not the only problem, but it's one of the major problems. And it's seen a few evolutions over the years, certainly since I started 25 years ago. but it still remains quite an issue. And we've tried to take those issues with the help, incidentally, of people from the industry. It's been a team effort. There's been some fantastic people, Mike O'Connor, Colin Pooley, Gary Mitchinson, and a few others that have stuck with us through thick and thin with this. So just to give you some idea of how, how serious the connector bit is, I was talking to Cable One in America, and we were on a call like this, and I was doing a presentation, and I said to them, I've heard you change out just about every single F connector in your network every 5 years. And the CTO there stood up and he said, no, Keith, you're miles out. It's every 2 years. So, there's various reasons why that is, but most operators end up doing the same. So let's start to look at where the evolution started. It started with the crimp connector. I'm sure there's a lot of people on this call that can see that crimp connector there. And it did a job, and it did a job for a long time. And then the next evolution came, and this is the compression connector, and that's the connector that we see today pretty much everywhere in terms of the interconnect. And then many years later to date, now comes the next generation game changer, which looks completely different to anything you can see in that picture. And what I want to do today is to explain to you what we've tried to achieve, where we've come from, and how we've achieved it with something that looks completely different, but utilizes a similar prep, but with a game change in addition to the prep, and certainly a different look to the connector. So what are the key elements to address? Well, first thing we had to do was stop being just a connector company. We had to step back and think completely outside the box, look at the issues above and beyond, and try to come up with some innovative solutions to that. So the one thing we wanted, simple to install connector using a single tool and mitigating all current connector issues, or certainly as many as we could. No more loose connectors. So we know that is one of the bugbears of any screw-on connector, is they can A, not be tightened properly, B, they come loose. And of course, when they come loose, you end up with lots of intriguing issues with loss of signal, RFI leakage. The RFI leakage is quite serious, of course, because one of the biggest assets a cable operator has is their biggest asset, relatively speaking, is their upstream. They've got the biggest two-way pipe available. And of course, if you get RFI leakage and you start to destroy the carrier to noise of the upstream signal, and you not only lose bandwidth, but you can damage the service as well. So Class A++ shielding, possibly without shielding possible without degradation over time. So we want the ultimate shielding possible from the interconnect with the cable and the connection, but we want it to stay like that forever, or as long as it needs to be connected. One part construction, maintaining optimized grounding from cable braiding to connector body. No continuity member, I'll come into that in a short time. And optimal metal to metal contact between the cable braiding and the full length of the connector ferrule post, giving you 360-degree contact pressure, giving you the ultimate grounding connection. And of course, hermetically seal, avoiding moisture and air, because a lot of operators today use unalloyed aluminium braided cable. And aluminium in its own right, if it reaches air and moisture, it goes into self-preservation mode and it starts to oxidize. And that oxidization layer doesn't conduct. So hence you have a bit of a catch-22 where the connector suddenly loses all its grounding and all the associated issues are shown then. So here's the three main grounding issues that we've addressed. So this is a standard connector today. So down at the bottom you can see a cable, number one, with the braiding showing. Number two is the post of the connector. And then number three is the nut that turns and locks the connector on. And what we're trying to do in reality today even is join number one to number two to provide as better and as most effective contact metal to metal contact as we possibly can, and then join number 2 to number 3, because that's in 2 halves as well. And then of course you end up with a 1-path continuous connection to the connector, so it makes the cable then seem seamless to the connector. That's what we've got today. Now, one of the issues that you can see, because part 2 and 3 are in 2 halves, what you'll see now if you watch this very short video is the connector isn't screwed onto anything at the moment, and now you can see the front half of the connector is separate to the back half of the connector, but you won't have any grounding if those 2 are not made as one or not joined as one. Here you can see it from the front, so you can see now the only time that is going to be connected from the front to the back is when that connector is screwed onto an F port, which you're going to see now. So basically just tighten up the connector. This is a standard connector used today, as has been used for many years, and I'll just finger tight that now. Now when you see the 2 halves, now you can see they're pretty much one, so we have continuity grounding right the way from the braiding to the front of the connector. But of course these connectors see extreme temperatures, they can get hot, cold, they expand, contract, and eventually they lose their torque and they come loose, and then of course you start to see relative issues where you're losing signal. So basically, as it's addressed, has been addressed, and is in some areas, is there became a thing called a continuity member. And if you look at the right-hand picture, you can see a red vertical connection. That is a spring that sits between the 2 halves of the nut and the body and pushes those 2 halves against each other to try and maintain a continuity, metal to metal contact. And it does so. And once that happens, your signal will be maintained, absolutely. But there is an issue of that the connector still can come loose. Now, when a connector comes loose without the continuity member, you immediately get intermittent faults, you get picture degradation, you get slow broadband, and in effect, it tells the operator to come and tighten it up again. And a lot of operators have schemes where they go out on preventive maintenance schemes and go out and tighten up all the connectors in America, up the poles, on the taps, everywhere. But of course, if you maintain the signal at this point and the connectors start to come loose, what you will see over time is a degradation in the upstream carrier to noise, because the connector still leaks. It does ingress and egress. And of course, egress is an issue because the government and authorities are clamping down on leakage. And of course, you don't want the opposite going up into your network. And the only time you know is when you've got hundreds of thousands of these things loose and your carrier to noise starts to degrade. And the only way you can fix that then is to go out everywhere and start tightening up connectors again. So I've pretty much covered what I've said on the left-hand side. The carrier to noise degrading is absolutely paramount that we stop that. So moving on now, when we make the grounding connection of an interconnect on a cable, it is compressed onto the connector via the jacket of the cable. And this is an example of a PVC cable used today by many operators around the world. It's a PVC cable, and if you put it under pressure, which I'm doing with the left-hand picture here, this is simulating the connector compressing onto the jacket to push the jacket onto the braiding, push the braiding onto the ferrule and make a grounding connection. When you let go, you have to put a lot of pressure on that PVC jacket, and you exceed its polymer tensile strength in most cases, in fact, in every case, and its elongation break percentage. And it basically flattens the polymer. And you can see in the right-hand picture that when we've let go of the pressure, the cable has stayed deformed. Now, of course, that what happens within the connector, and I'm going to show the end result of what happens here. So if this is how we started our research, so if the PVC jacket wasn't a PVC jacket, and it was a silicon jacket, for example, then you could put that pressure on and maintain that pressure and let go. You can see it springs back to where it started. So the pressure will be maintained within the connector if the jacket, for example, was a silicon material, not PVC. So here's an actual connector. It's the connector that you saw earlier. It's the real connector. And on the left-hand picture, I've ground the connector edge down to show what the inner part of a compression connector looks like. This is an Amphenol connector, so I've not taken anybody else's connector. This is similar to a lot of connectors. And you can see the two vertical red arrows. That's showing the compression point within the connector, where the connector is pushing onto the PVC jacket and then pushing itself onto the braiding, which is then making metal-to-metal contact with the post, the connector post. And then if we remove that section in effect and look at the right-hand picture, you can see clearly what has happened to the PVC jacket. But also important, you can see that the connector post, about 80% of it, the braiding is not being pushed onto the post at all. It's just sitting there. The only bit that's compressing is this bit here, where you can see the two arrows pushing onto the post. So if you leave that compressed and then you get these connectors going hot and cold, that gap that's being crushed will expand and contract. And then eventually, when it settles back down to a norm, there will be a total loss of pressure onto that braiding because the material, the PVC material, has suffered from creep. So in effect, you end up then with literally no pressure onto the braiding, onto the post. So, oops, sorry, I didn't mean to press that one. Just go back again. Getting ahead of myself. There we go. Sorry about that. Yeah, we'll get back to that one now. Right. So what we did was all compression connectors are a three-part construction. Okay, grounding from the nut to the connector, adding grounding continuity, remember we've discussed, lack of surface area pressure in the ferrule to the cable means poor grounding, metal to metal contact. So realistically now, if we move on, this is the sort of effects that you can see with ingress and egress, typical issues of loose connectors. Air gap suck out provides an impedance mismatch, and you can see the shadows and the reflections that you can get there on the picture I'm showing. Moisture migration out is another thing. Micro reflections, ghosting, reduced amplitude, interference, degraded MER, so that everything, all this results around the interconnect and the connector. So this is a typical loose connector scenario where it gradually gets worse and worse as the bit error rate increases to the effect you get a cliff edge effect where the picture has gone altogether. So this is the start of a truck roll. Probably the truck roll comes in the middle of that, or it goes straight to the cliff edge and they've got no signal whatsoever. Here's an example of the RFI shielding and transfer impedance of a typical jumper cable that you can see on the left-hand side. From the left to the bump in the middle, you can see that is the transfer impedance. So what that is in effect showing is the metal-to-metal contact resistance between the braiding and the connector. And then the right is the shielding effectiveness up to 3 gigahertz, and the red line, limit line, is class A++. So that's very, very good. If we can keep that, the bump in the middle is the crossover point. It's a software issue between the transfer impedance and shielding effectiveness of the chromic tube. So now, if we look at that cable on the left, it was made in 2004 and it was retested in April 2015. And you can see there's been quite a significant degradation in that cable. The transfer impedance has increased dramatically in the bottom end, and that's the start of CPD. It's the start of a grounding loss. It's the upstream nightmare. And then the right-hand side is the shielding effectiveness, which again is going. And what you find with this is it keeps going, it keeps degrading until eventually you have total failure. So we started to look for some ideas. So we know the PVC jacket is potentially an issue, and we know if we could do something over that braiding without putting the PVC jacket into tremendous force, then we can add pressure onto the braiding and keep it like that. So what we did was we created a one-piece connector. So there's no nut, it's a complete push fit with some very neat features. And we've removed the jacket over the braiding, the full length of the ferrule, which you don't do under normal circumstances. So this was the idea. Here's the start of the new connector evolution, this plastic weird looking thing. And what we've done is the two black bits on the left are silicon. They're silicon sleeve in each half of the shell of this new connector design. And then that will close and compress the silicon over the braiding directly, not exerting pressure onto the PVC sleeve. And then it closes and looks like the picture on the right. So this is what in effect it does. You push the connector, the cable in, and then you close the connector. This is the new idea, and you've got pressure applied, lovely grounding, hermetically sealed, and all good. However, there is a bit of a problem, because with a quarter prep, you fold the braiding back and it forms a leading that takes the post into the cable braiding. And without that, you have a bit of an issue of trying to get the post under the braiding. And of course, you end up like the bottom picture, stage 3, where it catches the braiding and distorts and completely trashes it in effect. So, and it would be a very, very complex scenario to do it that way. So the cable prep tool design will be complex. The assembly requires a bit higher skill. It exposes the braiding. This is a key one. It exposes the braiding, which risks contamination from your fingers, air and moisture during assembly. The last thing you want to apply to any aluminium-based product. And the two-part silicon sleeve could trap and expose braiding potentially. So we had a few issues, but this is where we started. And then lots and lots of meetings, conversations, engineering, brainstorming, etc. We came up with something absolutely game-changing. And I've got to say, you know, I've been involved in some very big projects in my life, including fighter aircraft radar and all sorts of complicated RF stuff. But this gave me the biggest satisfaction ever when we came up with this. So we had to come up with a way that we could still utilize silicon, avoid putting excess pressure onto the PVC jacket to get the pressure onto the braiding, and ideally keep a quarter prep somehow. So this is how we did it. We came up with an idea of applying 2 lateral slits into the PVC jacket. So you have a standard quarter prep, as you can see there in the left-hand picture. And then we put 2 slits, lateral slits, one either side on the PVC jacket, the length of the connector post. And this itself does some amazing things. So let's have a look at what it does. So on the left-hand picture, here's the cable, how it is, braiding, PVC jacket, it has a bonded foil. So when you try to put pressure on that, it is in effect a tin can that you're trying to crush completely. And you know how difficult that is in a tin can. If you get hold of it with your hand and try and crush it, to get pressure to go through 360 degrees to get that braiding onto the post, it's very, very difficult. And you can see that by the right-hand picture, which is showing all the pressure trying to crush this perfectly circular item with even the tin foil based bonded foil. So the thing takes a lot of pressure. Now, if you put the lateral slits in there, now look what you've got. The cable now has got the braiding undisturbed. but the jacket is in two halves and there's a slight gap. Now, if you put the post in there, you need nominal pressure on either side of the two parts of the jacket to apply the grounding pressure onto the braiding, onto the post. And you get 360-degree pressure with very little force whatsoever. So we need now to be able to close that, put the pressure on and keep it hermetically sealed. So we've got the slits, which work absolutely fantastic. So this is how we did it. So standard quarter prep, fold the braiding back. Now, the nice thing about folding the braiding back is it doesn't matter at that point if you've got contamination onto that bit of aluminium, because it's not doing anything. That the folded back braiding is only providing a lead-in to get the post into the braiding. And then basically you've got exactly the formulation you had before, but with the slits, you slide the post in now and it goes in super easy. You can assemble an RG11 connector with your little finger and your thumb and push the cable in. It's that easy. Whereas now, as you know, it's almost feet, arms, everything to try and get the connector, a post into an RG11. This is an RG59, RG6 example. So now what we've got to do is to seal that and put the pressure on. So here we go. So now we came up with the third major breakthrough, and that is to take the silicon out of the body of the connector. So you can see now it's gone, and put a fixed silicon sleeve onto the connector post body. And in the plastic, in the body, we've put some expansion release grooves in the side walls that allow the silicon to compress very easily without excessive force and not get trapped within the connector body when you close it. So this is what you do now. So there's the sleeve. By the way, the sleeve is transparent and it's colored. So red is 59, blue is 6, and clear is RG11. And you basically just prep the cable, slide it in. These are transparent, so you can actually, unfortunately, I couldn't do it on this. I'm not clever enough to make that bit transparent, but we got to the point where now you can see it nice. And when it seals now, once that closes, you have got a complete hermetic seal around the whole of the post and the cable. And the front end of the connector is hermetically sealed because it has a sliding pin mechanism. So now the whole thing is completely hermetically sealed. But more important, you have got a 360-degree compression area around the whole of the braiding onto the full length of the post. So the grounding is as good as you can possibly get. So here are the connectors in reality. Clear, as I said at the top, RG11, red and blue for 59 and 6. And then you can see that the colours through the opaque plastic body also. So when you go up to a connector, you know it's a 59, you know it's a 6, you know without even looking what is connected and what is not connected. The tool itself, the stripping tool, has been redesigned. So it does a standard quarter prep. The only addition is number 2 on the picture on the left-hand side, which is the 2 lateral slit cutting area. And that basically has to cut through the PVC and the foil. And then this is a video now of how the tool works. This is one of the earlier tools. I'll hold some of the latest ones up in my hand when we've finished. So this is how it works now. This is actually RG59. So it goes in as standard. This is myself doing this at arm's length. So if you see me shaking a little bit when I'm pulling the connector off, here we go. So you press the 2 levers at the top and you pull, and it's done a standard prep, but it's put the 2 lateral slits in as well. It's much easier when you can hold it close to you to do that. And pull the braiding back and push the connector on. Watch how easy this goes on. That's it. You can see physically it's gone all the way in, and then you just snap it shut with your fingers. Or if it's a bit hard, the cable, because it's cold, you can pop it in the back of the tool and just nip it up. As simple as that. That's the connector done, finished. And you'll see on the end of the connector, there's a neoprene seal as well. So when you push it onto the F connector, mating connector, it forms a hermetic seal at the front as well. So again, just another picture of the connector and how it can fit into the tool. On the left-hand side now, we've got the shearing effectiveness and transfer impedance with a normal connector. First time made, that's how it looks. Looks very good. But if you look at the right-hand picture, that's with the two lateral slits. And you'll see there that the shearing effectiveness has gone down from typically 105, it's gone down as low as 140-ish. That's because now we've got absolutely superb grounding due to the lateral slit that we've come up with on the prep. And when you put it through all the degradation testing of temperature, moisture, it stays like that. Then, of course, we come to the ring spring. This is another nice feature of having a push-on connector, because push-on connectors also have inherent issues. So basically, the main issue is if you come up with a very, very good push-on ring spring that has very good holding force, is terrific holding force, then when you push it on, you naturally want to twist it, because if anything feels hard to push on, you naturally just start to twist it to help it on. And if you do that, then the ring spring itself will start to grind against the threads of the connector, taking the plating off both the connector and the F mating connector, and coming up with grounding problems alone. So we have a very, very nice little system in the design of this. So watch what happens when we push this connector on and start to twist it. If you look there, the actual ring spring body of the connector isn't moving. The back of the connector, the plastic bit with the post connected into the cable is moving, but the ring spring front end doesn't move. So in effect, what happens is you're just pushing that on. You're not twisting it in any way. And in effect, as you're twisting the body, you're moving the connector post inside the braiding, and it also helps to maintain the grounding metal-to-metal contact. So a nice little addition. Here's an example of it from the front without a mating connector. I just grab it with my fingers, and you will see, look, you can see the black body of the connector moving and the front not. So that really makes a very, very nice feature where you can't damage the ring spring when you push the connector on or pull it off. So that was another bit of the innovation that we came up with. So in effect, here's another nice feature of the connector. As you know, when you disconnect from a device in the home, for example, or in the network to the home, you end up with one part of the grounding part of the connector in one hand and the potential grounding of the network in the other hand. And if something has gone wrong anywhere, I know there are isolators in the in-home in the UK, but they aren't in every country, then you could get a potential electric shock. With this, of course, the whole connector is plastic. There's no metal to touch, period. So you can take this connector, pull it off by hand, put it on by hand, holding both ends of the potential parts, and you are completely insulated. So again, a nice safety feature of this connector. This is the red dye sealing test. So this is horrendous. It's an SCTE US requirement, and it really is very, very difficult to meet. And this new innovation has gone through. Here they are on the end of the test cables, and they've come out of the dye test, and then we strip them down. So what we've done here on the right hand side is we've taken the connector off the back, taken it out, and you can see if any of the dye has got into the braiding, into the front end of the cable, and as you can see, it's lovely and clean. So the silicone jacket has done a very, very good job, and the front end seal as well. We've also then stripped it back, stripped the jacket clean off to see if it's got in anywhere into the braiding, into the dielectric, and it hasn't. So we've gone through this horrendous test, and it passes with flying colours. So in summary, we have a one-piece easy fit connector, quarter-quarter prep, no compression tool required, hermetically sealed front and back when the connector is left disconnected, optimized grounding connection, absolutely the full length of the ferrule using the unique lateral slit and the silicon compression sleeve, providing a total hermetic seal. Opaque see-through sleeves allow visibility of the connector during assembly, so you can see that you've got the cable completely in the connector. But also you can open these connectors and use them again. So you can open them, pull the cable out, and put a new one in if you wish. The cable easily pushes onto the post without distorting the cable braiding. Another important point, because the braiding is formed such to form the optimum screening, you don't want to squash it, crush it, bend it, and of course it slides in beautifully thanks to the lateral slits. We've optimized the ferrule of the connector to be specifically optimized to aluminium braided cable. So that is basically the galvanic, dissimilar metals, etc. So the ferrule, the post itself has a specific plating on it that is optimized to aluminium. And then of course we hermetically seal it to prevent air and moisture getting in there. The connector body rotating, protecting the ring spring from damage during installation is another key one. And of course, the safety of having of electric shock, having a plastic body is another added benefit. And no more loose connectors because we're using a push fit connector. So that's all. So the end result is hopefully no more intermittent faults, ideally, due to loose connectors and poor grounding. Guaranteed long-term RFI shielding effectiveness of A++ at least. Optimize RF signal connection between the connector and the cable. And this is another nice big benefit. On the left-hand side, what you see there are the tools required to do a current interconnect onto an RF cable in a cable network. And on the right-hand side is everything you need to do it with the new connector. Just one single tool and a connector. So it makes the whole thing so much simplistic compared to that. So I think we've managed to get through there. Hopefully people haven't fallen asleep and found it reasonably interesting. So that's the presentation.
Thank you, Keith. Yeah, definitely interesting. I just glanced back and so familiar with compression and yeah, completely different direction. So but no, it looks really well thought out. A couple of questions that have kind of dropped in again, but I suppose same ask to everyone. Anything you want to know, just drop it in the chat and we can obviously fill those questions out. We've got an opportunity to run through anything. Or if you'd rather ask them kind of in person, just raise your hand and we'll be able to give you the microphone, so to speak. But just to run through a few, I'm just going to read these out. So first one, we agree that the most important part of any RF transmission line is grounding. What effects have you seen on a HFC network whereby the connector cable grounding has degraded or even been lost altogether? Oh,
good question. Right, well, definitely I can answer this one because I've seen this in person, which was an incredible experience, actually. I was at a friend's house. It has full Virgin services there, and what it's like when you go around to friends, you're hoping to go out for a beer and they collar you to ask you some questions. And he said, the catch-up TV isn't working on our set-top box. And I had a look and I could see the modem light flashing on it, so I immediately thought the upstream signal's disconnected somehow. And I was able to get into the set-top to see what was going on in terms of its output, what it was ranging, frequency ranging, and it wasn't connecting to the upstream. So I said, it looks to me like probably the modem is more likely to be faulty. So you need to call out technicians. So he did, and I asked him, I said, when you do that, can you please let me know the day it's coming, because I'd like to come over and just sit as an instant party. And I did, and the technician came in, and he was very, very knowledgeable. I didn't let on I know anything or who I was. And he went straight to the connection at the back of the set-top, put his meter on to look at the upstream and downstream, and immediately just turned around to my friend and said, oh, the grounding's gone in the connector. And I thought, well, okay, I'm listening. So he cut the connector off both ends of the jumper, and he went outside and he cut the connector off and put a new connector on from the drop to the isolator. And he came in and he put it on the measurement system, and it was perfect. He connected it. So basically, the downstream was perfect, but the upstream had stopped working. And this was a grounding issue in the connector. And all I said to him was, oh, is that normal? He said, oh, absolutely, all the time. So I said, okay, that's good to know. And my friend was happy. And it's lasted a long time. He's had it a long time, but nevertheless, he said it has been getting worse and worse, where he thought, you start pressing the handset so hard, you're almost pushing the buttons out the back of it, because it's not doing what you hope it'll do. And of course, this was all down to the grounding degradation. And looking at it, we've looked at it, and it's a sort of common mode issue where the modem, in effect, your transmission line is no longer a transmission line, particularly the low frequency part of the upstream becomes an issue where your impedance has changed, you get micro reflections, the grounding's gone. So as a result of that, in effect, you've just got a load of mush, and the grounding's gone, boom. So that was the biggest and most realistic one I've seen. And when you talk to operators about this, they say, well, it costs the most to go out to a home to fix it. So to cut a connector off costs next to nothing. So we might as well just cut them all off. And in many operators around the world, that's just what they do. They go to a home. And if you're going out and you're changing a dollar splitter, then at the same time cut the connectors off and renew those as well while you're there. So this is all part and parcel of the day-to-day issues of losing grounding. I feel, in my humble opinion. And obviously now with the new connector, well, we're doing trials now, and time will tell. But certainly from the hardline testing we've done, this should help that problem tremendously.
Awesome. No, thank you. Very detailed answer. Another one in as well, I'll just reel out, obviously final call for anyone. You might get away quite easy from this one, Keith, which is always good. So just next question, threaded F ports on devices can vary considerably. They're affected by plating types and thickness, as well as tooling wear during manufacturing, which can affect the mating connector outer diameter. How does your push-on connector cater for this?
Oh, another good one. Right, very good question. And equally as important as treating the back of the connector is treating the front of the connector. And the threaded F connector is not ideal. You can imagine they're made in their millions. The dyes that are cutting the threads are ripping through these things constantly 24/7 in the factories in China, and the tolerances degrade. Then you add, once you've cut the thread, you then plate it, and the plating process itself is not as detailed as people think. So you end up with threads of all different diameters, pitches in terms of the pitch of the thread itself. And this also is one of the issues that causes loose connectors, or connectors that don't even tighten properly because of the thread. Also, you rip the plating off. If it's a tight connection, a very tight outer diameter, then when you put you screw the connector on, you tear off the plating, and the plating's part and parcel of the grounding interconnect. So what we've done here is with the ring spring in the new design isn't a sort of oval shape. It's slightly oval, but it's more flat. with ends that compress. And so basically we're pushing more, hitting more surface area of the thread. And of course, by not having any twisting whatsoever taking place onto the plating, we're not damaging the tip of the thread per se. But what we found also is that you can utilize this connection very, very well with no thread. So have a threadless F connector, and this has already started within the UK, for example. Virgin Media have some products now that are F connector threadless, designed for push fit connectors, and that then gives you the ultimate connection with a ring spring, because you're hitting the surface completely 360 degrees round rather than just the tips of a cut thread. So that's a very good question. Ideally, no thread, but with a thread, it's certainly as optimized as it could possibly be. And of course, it's not ever going to come loose. So the RFI screening will maintain a good shielding effectiveness.
Awesome, thank you. And once again, very detailed answer. So final call for any questions. Oh, there we go. One comes in just as I was about to wrap up. So one for you. Have you tested this in an environmental chamber and how did it fare?
Yes, we did. It's gone through tremendous aging processing, which is temperature dependent, ramping up and down in temperature, adding moisture, adding salt fog, all the usual tests that you would do with a standard compression connector, to the point whereby you've aged the connectors in simulation of some 20 years or more. So yes, it's gone through full environmental testing, and of course pre-testing before, pre-test and testing after, RF testing, full electrical testing, full mechanical testing. So yes, it has gone through full environmental testing.
And a follow up to that just dropped in. And was it still class A++?
Yes.
Nice answer. There we go. Final call for anyone, just before I wrap up, just whilst we wait for that. Obviously on behalf of the society and membership, thank you very much. Really interesting presentation again. Obviously, if there's any post questions, by all means, we can collate those and get them to you and try to get answers back. But obviously, final call for anyone here and now. Just regards next for the and actually hitting the final kind of furlong of the spring lecture. Short break again now, and we'll be reconvening at 3 p.m. Where we'll hear from Mathis Bomertz on the topic of from continuous integration to continuous deployment using System Link to close the gap. And Mathis is obviously from National Instruments. So obviously do what you need for the next hour, and hopefully you'll be rejoining us from 3 p.m. But once again, thank you, Keith.
You're welcome. Thank you.
Awesome. Thank you all, and see you at 3.